Hello everyone. In this video, we will continue to further discuss topic D.2, stellar characteristics and stellar evolution, in particular focusing on late stage, very high mass stellar evolution, black holes, and the Chandrasekhar and Oppenheimer-Volkoff limit. For originator stars greater than or equal to about 21 solar masses, the core of that star is bigger or will be bigger than 3 solar masses, which is the Oppenheimer-Volkoff limit. If that core is bigger than 3 solar masses, it becomes a black hole. Um, in this section, we will discuss black holes produced by this mechanism, by the end-stage lifetime of a very high-mass star. It's worth noting there is another class of black hole called supermassive black holes that are about 1 million times more massive, and they form via a different mechanism, which we will discuss at a later point. So, after the core sort of collapses in the process of a supernova, if that core is larger than 3 solar masses, it continues to collapse, overcoming the neutron degeneracy pressure we discussed in the last video to become a singularity, a point of infinite density. This particular point bends space-time, if you recall our discussion of general relativity. And so within the event horizon, what is called the event horizon, or the Schwarzschild radius, light cannot escape. It cannot reach escape velocity due to gravity, where it's worth noting that we are making use of general relativity. The idea is that the center of the black hole, or the black hole, bends space-time around it, and so a straight line in that curved space-time, otherwise known as a geodesic, leads back to the black hole. As a result, they're black, and you cannot see them. So we can see here the comparison between different objects. A star has very, very weak lensing effects, so the photons travel essentially in straight lines. But as the stellar remnant gets denser and denser, from neutron star to a more dense neutron star and ultimately to a black hole, it becomes black, so to speak. So photons follow paths that curve back into the black hole so that no light escapes. So, properties of the black hole to know, black holes to know, is that they are known as singularities. That infinitely dense point at the center is strictly speaking the black hole. And then the event horizon, though, we usually consider to be the radius of the black hole. And so there's a little bit of ambiguity here about what you mean when you say the black hole. Do you mean the fixed event horizon around the singularity, or do you mean the singularity itself? Just be sure to clarify. There is very, very good indirect evidence for both stellar mass, that is, the kind of black holes we're talking about, that result from core collapse supernova, as well as supermassive black holes. And we will discuss this here. The evidence for stellar mass black holes includes the phenomenon of gravitational lensing. Light, according to general relativity, can be deflected by an object of sufficient mass. And because of that deflection, the star will appear to be somewhere it is not actually. Mostly because when we detect light, we cannot see that it had bent, so it appears to come from somewhere else. This produces phenomena known as Einstein rings, and this is the a graphical representation, this is not actually an image, of a black hole lensing a galaxy behind it. And you can see that the light sort of bends around that black hole, producing the Einstein ring. We also have evidence from accretion disks for both supermassive black holes and for stellar mass black holes, seen here. These accretion disks happen when the black hole is sort of pulling in material from somewhere else, sometimes a companion star, and then as that material falls into the black hole, it can sort of rub up against each other and become very hot. This shines very brightly, sometimes in the visible in UV, but oftentimes, more often in the X-ray. So we can see stellar mass black holes because the accretion disk around them produces X-rays. And then for supermassive black holes, you find that, or you can find incredibly good evidence by examining a place called Sagittarius A star, which is in the middle of the Sagittarius constellation. And we've actually seen stars sort of swing around a very, very, very massive and invisible point right at the center. And it turns out this point is the center of the Milky Way. And if you do the math on the mass it would have to have to produce these orbits of the stars as they go around that supermassive black hole, you come up with a mass of uh, roughly 1 million times the size of the sun, the mass of the sun. And that is the supermassive black hole at the center of the Milky Way. This is very, very good evidence that these black holes exist.